This is John Whitaker for the Probability Graduate Level class, and this is our third video lecture. And today we want to continue on discussing conditional probabilities. We're going to look at something called the multiplication rule, which is an extension of a fact that we ended with from lecture 2. We're also going to look at Bayes' theorem and an extension of Bayes' theorem, and we'll finally conclude with first looking at independent events. Well, that having been said, let us recall one of the latter facts that we have dealing with conditional probability, and that is that the probability of A intersect B for two events, that equals the probability of A given B times the probability of B. And this is a way, a lot of times, a useful formula for calculating the probability of the intersection of events, where this type of conditional probability might be easy to calculate. And so that's our formula. We want to extend this. So here's the way that we'll extend it. We'll say, this is called, it's a fact, it's called the multiplication rule. Some people call it the multiplication rule. And what it says is the following. It says, let E1, E2, all the way up to En be events. Then the probability of E1 and E2 happening and E3 intersected with all the way up to En, that can be thought of similarly to this, is equal to the probability of E1 occurring times the probability that E2 occurred given that E1 occurred, times the probability that E3 occurred given that E1 and E2 occurred, times, and we'll keep going, all the way times the probability that the last event happens given that the previous n-1 events occurred. So that's the multiplication rule. We'll do an example of it in just a second. I think I got it all down there. But first we're going to prove it. And the proof is easy. If you start, this is a formula, and really what we're going to do is we're just going to start with the right-hand side of that formula. So, as a proof, if we look at, well, I guess we'll say let E1 all the way up to En be events, then the probability of E1 times the probability of E2 given E1 times the probability of E3 given E1 intersect E2 times all the way up to times the probability of En given E1 intersect E2 intersect all the way up to the intersection of En minus 1. What that's equal to the probability of E1. And then the conditional probability here, by definition, of conditional probability is equal to the probability of E2 intersect E1 over the probability of E1 times here, this will be the probability of E1 intersect E2 intersect E3 is one way of writing that. First part of the definition, top part of the definition of this conditional probability, over the probability of E1 intersect E2. And we keep multiplying this out. And the last thing we have is the probability of E1 intersect E2 intersect all the way up to the intersection of En minus 1. Intersect En. So remember, the conditional probability of one thing given another event is the intersection between these two events over the probability of the given. So that's the probability of E1 intersect E2 intersect all the way up to E to N minus 1. And then if we look at this, what we see is this probability of E1 cancels out with the probability of E1 that's in the top. So the common factors top and bottom cancel out. the probability of E1 intersect E2 or E2 intersect E1, that probability is the same thing as probability E1 intersect E2, so they cancel out, just leaving the probability of the intersection between the first three events. But there's always going to be cancellation between the previous top's fraction and the next guy's bottom. And so what's left is just the last guy's top. And so that's equal to the probability of E1 intersect E2 intersect E3 intersect all the way up to the intersection of E1. And that's what we said was the formula. So we have this quantity is equal to that. That's what we're trying to do. Well, that having been done, let us look at an example. So let's say an urn has 8 white balls. So the same example we had before in terms of the setup. And 3 red balls. Let 3 balls be chosen at random. And then we'll let that be done without replacement. And the question is find the probability that the first ball is, red. The second ball is white. And the third ball is white. Okay. So we're going to use this multiplication rule. So the probability I'm going to denote this. First is red. I'm going to put comma. And comma means intersection. That's intersection. The second is white, comma, that's the intersection. And the third is white. So what we can think of using multiplication rules, this is the same thing as probability that the first is red times the probability that the second is white given that the first is red times the probability that the third is white given the first is red and second is white. Okay, so we need to compute each one of these. I am going to do this on the next board, and we're going to take our time in terms of calculating this. So that's equal to, well, the probability that the first is red, so let's see, there were 3 red and 8 white. So the way that can happen is, first of all, I get a red, and then it doesn't matter what happens afterwards. So with 10 balls left, we're doing it without replacement, and then 9 over the number of ways of getting 3 balls, and there were 11, 10, 9. Times. Now, the probability that the second is white, given that the first is red. So let's put ourselves in that position. So the probability that the second is white, given that the first is red, well, there's 8 white balls to choose from, and then we have to choose another ball, and there would be 9 balls to choose from after that. And then, given that the first ball is red, we have 10 balls to choose from, and then 9. And then the probability that the third is white, given that the first and second, first is red and second is white. What that is going to be 7 ways of choosing that ball, putting ourselves in that position. Out of here we would have, let's say we've chosen 2 balls, so it would be 9. And so this is the same thing. It's 3 out of 11 times 8 out of 10 times 7 out of 9. And that's the answer. So let me make sure I didn't make a mistake. So 3 out of 11, 8 out of 10, and 7 out of 9. Yes, that's correct. Okay. The next thing I want to give to you is a comment that it's illustrated in this problem. And we said it in lecture 2. Often finding conditional probability is not difficult, especially when you're being asked to find out what happens next, given what happened previously. Okay? So we need to keep that in mind. But as a comment, let me write this down. And we'll use this a little later. But the wording for conditional probability, the percentage of A that is B denotes the probability of B given A. So it's conditional probability. That's what that denotes. So that's something to keep in mind, as well as the information that I just gave you about it being easy sometimes to compute conditional probabilities by putting yourself into the given situation, especially when you're being asked to compute the probability of what happens next, given what happened previously. But what if you're not in that situation? Well, we have a theorem called Bayes' theorem. So let me write down what Bayes' theorem says. It says let A and B be events with the probability of A being greater than 0 and the probability of B being greater than 0. Then the probability of B given A, well, let's say of A given B. No, I'll write down the just to keep matching my notes. So B given A is equal to the probability of A given B times the probability of B all over the exact same thing, the probability of A, at least initially, A given B times the probability of B, but then plus, in the bottom, the probability of A given B complement times the probability of B complement. Get out of the way, let everybody have a chance to write that down. And we'll prove that. And then do an example. Okay. So the proof. Well, the probability of B given A, that's the left-hand side was Bayes' theorem. By definition, that's the probability of B intersect A over the probability of A. And that's equal to the probability of A intersect B, I'll rewrite that up that way, over the probability. Now, the probability of A is really the probability of A intersect B union A intersect B complement. So I'll stop there, and I won't say very much about that. I'll show a picture in the generalized Bayes theorem proof a little later to explain that. But that's what this is. The total law of probability is where I'll really show it. The probability of A intersect B, by our fact that we ended lecture 2 with and began this lecture with, that can be thought of as the probability of A given B times the probability of B. Now, here I need any parentheses. The probability of A intersect B union with A intersect B complement. So here, this is nothing more than two mutually exclusive events in your union. So that's the probability of A intersect B plus the probability of A intersect B complement. Well, that's equal to, again, using that fact that we started recalling in this lecture here. This is the probability of A given B times the probability of B plus, here, this is the probability of A given B complement times the probability of B complement. And that's what we were trying to show that the probability of B given A is equal to. So that concludes the proof of Bayes' theorem. Okay, let's look at an example. And let's go back to that same setup as what we had before with the urn. So as an example, suppose an urn has 8 white balls and 3 red balls. So 2 balls are selected. One after another, without replacement. Random. Okay. Find the probability that the first ball selected is white, given that the second ball is red. All right, so that's our problem. And this is a little different scenario than what we had before, where I said it's quite often easy to compute a conditional probability. It's easy when the sample space is filled with equally likely events and you're asked to find what happens next, given what happened previously. But that's not what we have here. We're asked to find the probability of what happened previously, given what happened next. And so we'd like to switch that, and that's what Bayes' theorem allows us to do. So here, note the probability that the first is white, given second is red. What that's equal to by Bayes' theorem is the probability that the second is red, switching, given first is white, times the probability that the first is white. Okay. All over this exact same thing. The probability that second is red, given first is white, times the probability that the first is white, plus, now it's the probability the second is red, given, and now it's supposed to be the opposite of the first is white. So the opposite of the first is white is the first is red, times the probability the first is red. Okay, I'm going to do these over here. So we got one. So this is, the top part is a conditional probability that I can put myself in the position. So the first ball we selected was white. That means now we have 7 white balls and 3 reds. And so the chance that we got a red is 3 out of 10 times. The probability that the first ball is white is 8 out of 11. And then I just write down that exactly down here. So 3 out of 10 times 8 out of 11. Plus, now, this conditional probability that the second is red given the first is red. So we have taken out a red ball, and that means we have 10 balls left, and exactly 2 of them are red. So 2 out of 10 times the probability the first is red. Well, that's 3 out of 11. And so that's the answer. Let me check, make sure I didn't make a mistake. It's 3 out of 10 times 8 out of 11, and then 3 out of 10, 8 out of 11 at the bottom, plus 2 out of 10, 3 out of 11. That's correct. So that's using Bayes there. Okay. So next I want to turn to a definition of something called a collection of mutually exclusive and exhaustive sets. So we're going to let E1, E2, E3, all the way up to En be events. Then E1, E2, all the way up to En are said to be mutually exclusive and exhaustive if the following holds. So the first part, you've seen mutually exclusive before. It's in the definition of probability. That is, mutually exclusive is that EI intersect EJ is equal to the empty set for I being different than J. Anytime you intersect two distinct events from this collection, you get the empty set. They have no overlap. 2, here's the exhaustive part. If you union up I running from 1 to n of the EIs, you get the sample space. So what we mean by exhaustive is that the sample space is being broken down into these E1 through En, and if you union them up, you get the whole sample space. Okay? Way of partitioning up the sample space into non-overlapping regions where the whole sample space is held. I want to go over a fact called the total law of probability next, and it was kind of involved in the proof of Bayes' theorem. So here's what it says as a theorem. It's called the total law of probability. Says, let E1, E2, all the way up to En be a collection of events that are mutually exclusive and exhaustive. Let A be an event. Then the probability of A is equal to the probability of A intersect E1 plus the probability of A intersect E2 plus the probability of A intersect En. And so we will prove this, but first we'll draw a picture, a Venn diagram that kind of helps us see what this is. So we think of this box being the sample space. We got a set A. That's A. We're trying to figure out the probability of A, the worth of A, if we think of it as a piece of property. Then, if we have these, if you will, other events, E1, maybe there's E2, maybe this is E3 right there. This is E4, and we continue on till we get right here to maybe this En right here. Continued on, we got to En. Then what's clear is that if you want the worth of A with these mutually exclusive and exhaustive events, the worth of A is the part of A that's in E1 plus the part of A that's in E2 plus the worth of the part of A that's in E3 and so forth. And so that kind of helps us see that this should be the formula we get. So here's the proof. So the probability of A, well, is equal to the probability, again, we could say, rewrite A as A intersect E1, union with A intersect E2, union, all the way up to union up, A intersect En. And what happens is that you can see by the picture, it really comes from the fact that E1, I'm sorry, this equality, let me give a little bit more explanation here. This equality comes from the fact that the sequence of events E1 through En are exhaustive. Okay? So that's how we do this. Now, because the E1 through Ens are mutually exclusive, it makes A intersect E1, A intersect E2, and A intersect En all the way in between those types of sets be mutually exclusive. And since we're unioning up the mutually exclusive events and taking the probability of that union, okay, then what happens is that that is equal to, by the definition of a probability, that's the probability of the first one plus the probability of the second set plus, and you continue on all the way up to the probability of the last set. And that's what we try to, that's what we want to prove. So that ends the proof. Now, what I want to do next is write up Bayes' theorem, an extension for it. So here's what it says. So here's the theorem. Bayes' theorem, extension. Here's what it says. It says, let E1, E2, all the way to En be mutually exclusive and exhaustive. Let A be an event. I should say events here. Let A be an event. Then probability of E1 given A is equal to the probability of A given E1 times the probability of E1 all over. Okay. The bottom has the first exact same thing, probability of A given E1 times the probability of E1, plus the next part is probability of A given E2 times the probability of E2. Plus, and we keep going in that fashion, and the last term that's involved is the probability of A given En times the probability of En. We'll prove this. Okay, so here's the proof, and we're going to let E1 up to N be mutually exclusive and exhaustive events. I'm going to let A be an event. Now, the probability of E1 given A is equal to, okay, by definition, this is the probability of E1 intersect A over the probability of A, which I'll rewrite as the probability of A intersect E1 over the probability of A. Now, using that fact that we started today's lecture recalling, the top can be rewritten as probability of A given E1 times the probability of E1 all over. The bottom, using the total law of probability with these mutually exclusive events and exhaustive events, is the probability of A intersect E1 plus the probability of A intersect E2 plus, and keep going all the way up to the addition of A intersect En. Now, for each one of these probabilities of an intersection, we can rewrite them by the same factors we wrote at the top as a conditional probability. And that is the bottom right here, becomes the probability of A intersect E1 becomes the probability of A given E1 times the probability of E1 plus the probability of A intersect E2 becomes the probability of A given E2 times the probability of E2 plus, keep going all the way up to the probability of A given En and then times the probability of En. And that is indeed what we're wanting to show. So that concludes the proof. It's a short proof. Now I want to do an example. An example I want to do, it's a little bit lengthy to write down, and it involves that comment that I made earlier. So here's the problem. So it's an example. There's a total of 46% of the voters of a certain city classify themselves as independents Whereas 30% classify themselves as liberals. And 24% classify themselves as conservatives. In a recent election, %35% of the independents uh, 62% of the liberals, and 58% of the conservatives voted. Okay? A voter is chosen at random. At random. So voter is chosen at random. Okay? And here's the question. Given that the voter voted in the local election, find the probability that he or she is independent. Okay, so wordy problem, and here's what the problem is telling me, and here's what the problem is asking me. So I'm reading, because it's on the other side of the board, but it said a total of 46% of the voters of a certain city classified themselves as independent. That's the first part of the sentence. So our sample space is the voters of a certain city. Not the ones who voted in a local election, but just the general people who are eligible from that city to vote. And so it says that 46% of those people are independent. So the probability of independent is 0.46. Also from the problem, the probability of when you just pick somebody at random as being liberal, that's 30%, so it's 0.3 or 0.30. And the probability of conservative, that was equal to 24%, so 0.24. Let's make sure this adds up to 100 or 1. Yes, it does. Also, it was given, and next line, let me get out of the way just a little bit. It says, in a recent election, 35% of the independents, so 35% of the independents. So they're telling us that given you were independent, so that comes to the comment that I made, the chance that you voted was 35%, so 0.35. Also, the probability that you voted given that you were liberal is 62%, 0.62, and the probability that you voted given that you were conservative, that's 0.58, that's said in the problem. Now look at what's being asked. It says you chose a voter at random, so someone who's in the population, chosen them at random. And then it says, given that the voter voted in local elections, so the probability, given that they voted, that's what I'm being asked. Let me write it here. The probability, given that they voted, what's the chance that they were independent? So that's what's being asked. And what I'm given is the conditional probability that they voted, given that they were independent. I'm asked to switch that. What allows me to switch that conditional probability is Bayes' theorem. So the probability of an independent given voter, what that should be equal to is the probability of voter that they voted given that they were independent times the probability that they were independent over the probability that they voted given that they were independent times the probability that they were independent. And what I need is I need to have a sequence of mutually exclusive and exhaustive events. What those are in this problem are the independent, are the liberals, and the conservatives. So that's what you are here, voter. So plus this probability that you voted, given that you were liberal, times the probability that you were liberal, plus the probability that you voted, given you were conservative, times the probability that you were conservative. Let me stick in the numbers for that. I just ran out of room. And then that will conclude the problem. So numerically, what I get for an answer is this is equal to, okay, so probability of voting given independent, 0.35. Probability of being independent was 0.46. This is over 0.35 times 0.46 plus the probability that you voted given that you were liberal, that's 0.62 times the probability that you were liberal, that's 0.30 plus, finally, the probability that you voted that you were conservative, that's 0.58, and the probability that you were conservative is 0.24. That multiplication and division gives you the answer to the problem. Well, the next thing I want to cover is a definition of independent events. Okay? So, two events, A and B, are said to be independent if the probability of A intersect B is equal to the probability of A times the probability of B. I'm going to do a fact and then two examples of independence. One more definition as well. And then we'll be done. So here, as fact, says if the probability of B is greater than 0, and A and B are independent events, then the probability of A given B is equal to the probability of A. And that fact kind of really captures the idea of A and B being independent. So the probability that A happened, given that you know that B happened, is just the probability that A happened. The fact that B happened didn't influence the chance that A would occur. Okay? So let's do a proof of that. So here, we're going to let the probability of B be greater than 0, and A and B be independent events. This is very easy. Then, the probability of A given B, by definition, is nothing more than the probability of A intersect B over the probability of B. But since A and B are independent, that's equal to the probability of A times the probability of B, by definition, over the probability of B, and of course the numbers, the probability of B over the probability of B, yield 1, so we just have the probability of A. That's what we want to do. Okay, one more definition, two examples, two quick examples, and then we're done. So as a definition, two events, A and B, are said to be dependent events if they are not independent events. Let's look at the two examples. Okay, so a coin is tossed in a die roll. Let's let A be the event that a head occurred. Let B be the event that a 3 occurred. The heads on the coin toss, the 3 from the die roll. Are A and B independent? Let's take our time, let's look at the sample space, see if we can figure this out. Okay. So, first off, for the sample space, remember we're flipping a coin and then rolling a die. So there's 2 outcomes for the coin toss, and for each one of those possible outcomes, there's 6 outcomes. So there's 12 in the sample space. And they are heads 1, heads 2, heads 3, heads 4, heads 5, and heads 6. And then the other 6, of course, are tails 1, tails 2, tails 3, tails 4, tails 5, and tails 6. That's what I'll represent the collection of outcomes. And then, so the probability to determine whether A and B are independent or dependent. I look from the definition. Probability of A intersect B, that's equal to the probability of, so what was A? That's probability of heads and 3. That's equal to the probability of exactly H3. Well, how many ways can H3 happen? It happens one way out of the 12 possibilities. Now, the probability of A, that's equal to probability of the heads the way that you can get ahead, there are 6 of them out of 12, so that's 1/2. The probability of B, that's the probability of the 3, and the way the number of outcomes that have 3s in them are 2 out of 12, that's 1/6. So since the probability of A intersect B in this case, which is equal to 1/12, equals to the probability of A, which is 1/2, times the probability of B, which is 1/6. Then A and B are independent. Okay, let's do one more sample. A die is rolled twice. Okay. Let E1, E sub 1, be the event that the sum of the die, the sum of the rolls, is 6. And E2, E sub 2, be the event that the first die roll is a 4. Are E1 and E2 independent events? Okay. So just as a quick reminder, the sample space would look something like 1, 1 all the way up to 1, 6. 2, 1 all the way up to 2, 6. 3, 1 all the way up to 3, 6. 4, 1 all the way up to 4, 6. 5, 1 all the way up to 5, 6. And 6, 1 all the way up to 6, 6. Now, I want to know if these two guys are independent or not. So the probability of E1 intersecting 2 is really the probability that the sum is 6 in the first die roll. First roll is 4. That's the same thing as the probability of getting 2, 4. I'm sorry, 4, 2. And that's 1 out of 36. The probability of E1 is the probability that the sum is 6. So let me think. In the first row of my outcomes over here, can I get a sum of 6? Yes. And how many ways can that happen? 1. Can it happen here? Yes. It's the outcome 2, 4. Yes, it can happen. So there's only one way it happens in this row. It's 3, 3. 4, 2. 5, 1. That's that one. There's no way in the last one to have it happen. So there's 5 ways out of 36. The probability of E2, well, let's do it over here. The probability of E2 is equal to the probability of first roll is 4. That's 6 out of 36. So note the probability of E1 intersect E2 does not equal to the probability of E1 times the probability of E2. So E1 and E2 are dependent events. That means not independent. Okay, that's enough for this video lecture. Thank you very much for your time and patience.